Thank you. So, annyeonghaseyo. Thank you very much for having me. And so this is some work. It's very much work in progress, but I'm very excited about it. It's work where I want to point out my collaborators. Sylvain Fichet is a postdoc at ICTP in Brazil who has done a lot of the theoretical framework for this. And these last three here, Lexi, Kuntal, and Ian, excuse me, are students with me at UCR. So here is the general idea that I want to present. So we want to study a dark sector. So in this dark sector, we have an extra dimension. It's a warped extra dimension. So here's the extra dimension. And the dark matter will be four-dimensional. So either on the ultraviolet brane or the infrared brane, it'll be purely four-dimensional. Ordinary matter, the standard model, is also four-dimensional. And the physics, the interesting physics will come from a scalar mediator, which will be a five-dimensional field. And the particular, so all of these ingredients are ingredients that we've had for model building for 2 decades at least. The particular thing which is somewhat new and interesting is what happens when we take into account large KK numbers, meaning many KK modes of the bulk field. And what will happen is that the narrow width approximation breaks down, and that'll end up leading to some rather interesting possibilities for phenomenology. And there'll be 2 particular things I want to talk about. One is this thing called the soft bomb. So this is what happens when the bulk mediator Cascade decays. And we will find that these processes are suppressed. And a second point, which will end up being related, is self-interacting dark matter with a fractional power potential. Okay, so that's the big idea. For those who are interested in jumping in here, there's been a lot of really interesting work over the past decade or so. And here is a somewhat incomplete list of a lot of the initial ideas along the lines of having either a warped dark sector or near-conformal sector for a mediator. But again, let me highlight this paper by Sylvain Fichet, which really lays down the theoretical framework that we are going off of in these studies. Okay, so I like graphic outlines. So this will be the outline of the talk. We're going to have a very quick general review of dark sectors and what we're doing. So when a lot of the dark matter folks like to talk about lampposts, so here's an old lamppost. Then we'll do a little bit of a review about the 5-dimensional theory. And this is a lamp that is called a hypercube. I found it on this website, Etsy. It's apparently for sale for $400, but when you see a lamp called hypercube, that's the icon for the lamppost for 5D dark sector. Then we're going to talk about this new phenomenon that Sylvain has taught us about called opacity. So this is when the 5th dimension becomes opaque, and I'll explain what that means. And the 2 applications will be these cascade decays and self-interactions. Okay, so let's start with the introduction and reminder of lampposts. So this is a sculpture or piece of art in the Los Angeles County Museum of Art. It's a bunch of old street lights that they put all together. And in dark matter model building, we like to talk about lampposts because it's this idea of if you're looking for something and you don't know where it is, like dark matter, you go somewhere where you have some kind of some framework for looking for it. And that is under a lamppost where you have some chance of seeing it. And we like to use this analogy for the different types of models that we assume dark matter might take. And I mention this mainly just to acknowledge that there are many types of lampposts, many different classes of theories of dark matter, and most of them, like the axion, I will not be talking about. I'm not addressing at all. So I'm not trying to say that one model is better than the other, but in fact, let me start with a particular lamppost that many have found is no longer interesting, but the weakly interacting massive particle, the somewhat original lamppost for dark matter. The weakly interacting massive particle, the way I want to define it is a dark matter candidate with a direct interaction with ordinary matter, with a standard model. This is because it typically comes from a beyond the standard model theory for Higgs naturalness. So the template is the MSSM, where you have a neutralino, and typically because of R parity, the neutralino is stable, and we have this WIMP miracle that this ends up for a large swath of parameter space giving you the correct relic abundance. And as many of you know, the WIMP as defined this way is an endangered species, there is a rich and well-established and well-developed experimental program for how to look for these, and large swaths of parameter space have already been ruled out. So I will move away from the WIMP, not to say that it's dead or is no longer interesting, but as a model builder, I have nothing to contribute for this particular lamppost for how to look for dark matter. There's a cousin of the WIMP, which is a dark sector. And this is the idea that maybe dark matter is completely inert, completely neutral with respect to the standard model. No gauge couplings, no Yukawa couplings to the Higgs. It's just completely separate. And the only way that dark matter interacts with the standard model is through an additional field, which we call the mediator. And what we typically assume is that there's only one or a few mediators, and that captures a wide range of dynamics from possible ultraviolet theories that could give basically this phenomenology. For a dark sector, which is a slightly more recent idea, there is also a fairly well-established but still richly evolving set of phenomenology. And the idea boils down to the fact that you have a mediator that has some spin, has some mass, so you have the quantum numbers here. And critically, it has some interaction strength with the dark sector, with dark matter, which is a green dot, and some interaction strength with the standard model, which I call a red dot. And you can look for things like the annihilation of dark matter, which is important for setting the relic abundance if you have thermal freeze out. So this only depends on the green interaction. And you can also explain why the traditional searches for dark matter might be avoided. So for example, direct detection, where dark matter bounces off of ordinary matter, or production in an accelerator where you produce the mediator and watch it decay. These are all things that are proportional to the standard model coupling. And so the typical game that we play with dark sectors is maybe this coupling happens to be very small and this coupling can be appreciable so that you can have some nice phenomenology, but also not be ruled out. And one relatively new thing that we'll get to later on in this talk is the presence of just this interaction, even if the standard model interaction is weak, may actually lead to observable signatures, which is the scattering of dark matter off of itself. And these are things which may have an impact on the density distribution in halos, for example. Okay, so this is just to motivate that there is a rich set of experiments and different ways to probe this general framework of dark matter that's not quite a WIMP, but it is an inert dark matter particle with some additional field. So that's the dark sector lamppost. In this talk, we're going to talk about a tweak of the dark sector lamppost. And the tweak is that the mediator now is a 5-dimensional field. So here's this $400 lamp. The 5-dimensional mediator is a bulk field. And the new phenomenon, the reason why we're talking about this now rather than 15 years ago, is that one notices that the behavior of many Kaluza-Klein modes can be qualitatively different from that of just a few mediators, meaning to say that a 5-dimensional dark sector behaves rather differently from just including 1 or 2 mediators. And this is a little bit surprising because a lot of our experience with 5-dimensional model building for, say, the naturalness of the Higgs does not prepare us for thinking about what do you do when you have hundreds of KK modes. Okay, so that's the background. That is contextualizing this particular class of models in the context of the entire range of different lampposts for theories of dark matter. Let's now say a little bit more about the 5th dimension. So the framework that we're using is a slice of 5-dimensional anti-de Sitter space. And of course, the reason why we mention this is because of the famous ADS-CFT correspondence, or the holographic principle, which states that this slice, this extra dimension, is dual to a strongly coupled near-conformal quantum field theory. So this space has a warped metric. So we're using conformal coordinates where this R is a length scale. It's the radius of curvature. So okay, here's a curvature. This is essentially a gravitational potential. So things want to fall towards the infrared, fall towards larger Z. The space is an interval. That's why we call it a slice of ADS5. And at position R, so R is very small, typically, the radius of curvature. So this is close to 0. There is an ultraviolet brane. This is a 4-dimensional slice where there could be dynamics. And at R, we call this R prime, or at 1 over some other scale, we have another brane called the IR brane. These two branes cut off the space. The dual description is that states that are near the ultraviolet, so at small distances, are elementary. They are like the partons in a confining gauge theory, and states towards the IR brane are composite. So these are more like pions or protons in confining gauge theory. And the dynamics in the bulk are approximately conformal. Like the breaking of conformal variance comes from the UV brane and the IR brane. So if you want, this is, most of what I'll have to say is purely on the ADS side. But if you want, this is actually a fairly modest modification of a dark sector. This is just a statement that perhaps the dark sector has strong coupling and approaches a quasi-conformal RG flow. This is something that is realized approximately in nature from QCD, so it's a plausible thing to imagine a hidden sector might do. So many of us are familiar with this general setup because this is one of the very popular models for new physics from the early 2000s. This is the Randall-Sundrum, well, the Randall-Sundrum 1 model, RS1. And this was a way to address the electroweak hierarchy. So I am mentioning this just to contrast what we'll be doing in this talk. In the RS model, the typical scale for the curvature is around the inverse Planck scale. This is a UV scale. And the scale of the infrared brane is inverse TeV. And the magic of the warped extra dimension is that states that live near the IR feel a warped down cutoff. So if you expect that the Higgs would get quantum corrections to its mass that would be on the order of m Planck due to, say, quantum gravity, then if the Higgs happens to be stuck on the infrared brane, the actual scale of these quantum gravity effects are the warped down Planck scale. So this Planck scale gets warped down for a field that's stuck on the IR brane, and you only get corrections in the order of TeV or tens of TeV. So that's the way in which this framework stabilizes the Higgs mass and addresses the electroweak hierarchy. And then people started playing games with this and started putting other fields in the bulk. It turns out if you put the fermions, for example, in the bulk, you can consider their zero modes. So now you're doing a Kaluza-Klein decomposition. So each of these curves corresponds to a 4-dimensional zero mode, a 4-dimensional field. And you notice that if the wave function or the profile of the zero mode happens to be leaning towards the UV brane, it has a very small overlap with the Higgs. So when the Higgs gets a VEV, the electron gets a relatively small mass because that mass is suppressed by the smallness of this overlap. Conversely, the top quark might be leaning towards the IR brane, so there's a big overlap with the Higgs, and when the Higgs gets a VEV, the top gets a large mass. And this now becomes quite a nice game for building models, and you can interpret this in terms of a dual description, and it's all really quite nice. You say that the top quark is an admixture of a little bit of elementary and a lot of composite. The electron is more of an elementary state with only a little bit of composite. Usually this is the way that we talk about Randall-Sundrum models, and then we say, oh, and then on top of the zero mode, there's a Kaluza-Klein mode. The Kaluza-Klein mode has some bulk mass and tends to fall in the gravitational potential and tends to lean towards the IR brane. And you can think about what the phenomenology is. And if we zoom back to 15 years ago, we were all thinking about what we would see at the LHC. And usually what we would focus on is how to discover the KK gluon, or the KK graviton, or the KK top. And we'd always talk about the KK top or the KK gluon as if there were only one. And of course, we know there's a tower of KK states, but because the cutoff here, because the infrared scale here is inverse TeV, we would expect that the LHC would only produce maybe the first KK mode. So only a few KK modes are relevant for the phenomenology. In contrast, the presentation that we have here, the warped dark sector, what we're calling the warped dark sector, is the same setup, but the infrared scale is now much lower. So as a number, I'm just going to toss in 100 MeV. Maybe it's 10 MeV, maybe something low, something much lower than the typical scale of a standard model process. Because this separation is what sets your periodicity. So this is completely analogous to a flat extra dimension or to a harmonic oscillator. The separation, this boundary condition at some finite length, sets the separation of the KK tower. If that separation is on the order of 100 MeV, then if I produce the mediator at some high scale, like at say 100 GeV, I am sensitive to many, many Kaluza-Klein modes of the mediator. And this is now the entry point to the phenomenon that we would like to play with in this idea. Okay, so that's the warp dark sector and how the warp dark sector is different from the RS1 model, right? I'm not going to make a big deal about where the dark matter or the standard model is, but typically I'll assume that the standard model is stuck on the ultraviolet brane as some elementary state. And the dark matter can be in either, but let's also put it on the UV brane. Okay, so everything I've just said, we've had the tools to talk about that theory for at least 20 years. What is new? So what's neat is a something that's been articulated fairly recently by my colleague Sylvain Fichet. So I strongly recommend starting with this paper for those who are interested in digging deeper. This is an observation that he calls opacity. It's something which had been well understood in the Euclidean space version of ADS-CFT, but something which he was really the first person to adapt to the Lorentzian spacetime. And a good starting point is to remember that any 5-dimensional theory is non-normalizable. So the theory is defined with a cutoff at which the 5D theory, meaning this entire picture, breaks down. So we should never be talking about energies beyond this cutoff within a particular effective theory. There's a little window between this cutoff and the curvature scale where the behavior of the theory is essentially flat because your probing distance is smaller than the radius of curvature. But for the most part, in this range, if you're probing the theory at energies up here, you're seeing many KK modes. And if you're probing the theory at energies down here, you're seeing only the first few KK modes. Right? This is now completely analogous to the Randall-Sundrum model with a cutoff at the TeV scale compared to our warp dark sector where the cutoff is around, say, 100 MeV, or something low compared to the standard model. Below this scale mu, you're not producing any KK modes on shell, and the effect of the extra dimension is to induce contact interactions on the brain. The key point, the key observation, and exactly the key point of the Randall-Sundrum model is that this cutoff is also warped down. So the cutoff on the UV brane is higher than the cutoff at the IR brane. Right? This is the idea that the quantum corrections to the Higgs loops on the IR brane should not be M Planck scale, but should be on the order of 10 TeV scale. And one can see this relatively straightforwardly. If you say that the typical separation, the typical length scale that you probe should be bigger than the inverse cutoff, then the metric shows up. And with the metric, you get factors of the curvature. So I keep going back and forth in notation, but the curvature is equal to the radius of curvature inverse. This is the prefactor. This R is the one that shows up in your metric. And you end up saying that you should only be looking at length scales larger than this inverse energy scale. And this inverse energy scale is position dependent in the extra dimension. Right? This is all perfectly standard. We can reinterpret this from the effective field theory perspective, 5-dimensional EFT. And we can say that higher order terms would become significant at momenta above some position dependent scale. You can imagine putting in some higher dimensional kinetic term. And so you get this factor of partial squared over the cutoff squared. And for momenta that are now larger than this scale, you end up going beyond the regime of validity of your EFT. So this is an upper limit on any momentum existing at some position. Now, we can take this qualitative observation and interpret it the other way around and say, if I produce a state of some fixed 4 momentum P, then this condition is a limit on the distance in the extra dimension with which this I should be able to probe. So if I produce something on the UV brane, how far down along the warped extra dimension should I be allowed to have a correlation function before it exponentially suppresses? This interpretation is something that should be familiar to you from ordinary 4-dimensional QFT. So you know, for example, if you're looking at the hydrogen atom or positronium, that when you have two particles exchange some bosonic mediator, there is a long-range potential. And the long-range potential that you feel is just the Fourier transform of this amplitude. But by virtue of this Fourier transform factor, the momentum that is exchanged, so here is the space-like momentum, tells you something about the distance over which this propagation is unsuppressed, right? Because this q, which is the square root of q squared, is imaginary. This will end up being e to the minus positive number times r. And that tells you that ends up being, so when you put in the amplitude, that ends up being precisely the Yukawa suppression, the e to the minus m mediator r. That tells you that the Yukawa force has a characteristic range when this mediator has a mass. So with that in mind, so this is just hand-wavy motivation from space-like momentum. With that in mind, we can look again at this condition that for a fixed momentum, it makes sense that there would be some condition on how far in the extra dimension you can traverse. So I should be very clear about this. These are two separate ideas. On top is a qualitative motivation based on 4 dimensions. And the bottom, again, is this EFT concept that if you have some given momentum, there is some maximum propagation in the extra dimension before which you seem to be falling outside of the regime of your EFT. And then we notice that if I put in the infrared brane in this equation, so Z, the infrared brane is located at mu inverse, so mu is an energy scale, then you have a condition for the maximum momentum that could possibly, and again, everything here I'm saying is hand wavy, but this is the maximum momentum that seems like it could plausibly hit the infrared brane. So anything that I produce on the ultraviolet brane with momentum bigger than this scale seems to be in a bit of a paradox. It seems like it should not be able to reach the infrared brane. So without actually proving this rigorously, and again, I point back to Sylvain's paper, but just to motivate this concept, it seems like we have split the energy scales here. So for sufficiently low momenta, the extra dimension behaves in exactly the way that we're taught when we first do the harmonic oscillator. It's Randall syndrome 1-like, where you have this discrete set of Kaluza-Klein modes, and each of those Kaluza-Klein modes has a characteristic energy that is able to propagate down the throat, down the warped extra dimension, and know about the IR brane. I can ask about correlation functions between the UV brane and the IR brane, because the characteristic momentum doesn't go above this scale, which seems to be given to us from the effective theory point of view. In this regime, something interesting seems to happen. In this regime, what I seem to be saying is that there is some characteristic region in the infrared of the extra dimension that my probes in this that are located in the UV brane should not be able to reach. It's analogous to saying that there's like a Yukawa suppression, that a correlation function, a 2-point function between here and here should exponentially die off because the characteristic momentum that is flowing would be beyond the cutoff in this regime of the theory. It's beyond the warped down EFT cutoff of the 5D theory. And so now let me just add more words to the scaffolding. This is as if the infrared brane is invisible to probes that start on the UV brane and have momenta above this scale. And if there's no IR brane, this is like the RS2 model. So this is this IR brane was important for setting the boundary condition that set the periodicity of your discrete Kaluza-Klein spectrum. And so if there's no IR brane, if above a certain momentum, you're not sensitive to the physics of what's happening down here, then you might expect that you end up with a continuum of states rather than a discrete KK tower. So this is all a qualitative description of what Sylvain has worked out much more methodically. But let me skip the methodology and stick with just the qualitative behavior and present what seems like a puzzle. So what the puzzle is, my qualitative motivation for this came from intuition from space-like separation, where the characteristic momentum scale being transferred gives me a scale here, and this becomes a real number with an exponential suppression, gives a characteristic scale from which you can expect the force to be active. What happens when that characteristic momentum is time-like, meaning it's on shell? So I can actually imagine at the LHC or some linear collider, I produce a mediator at high energy, so well above this scale. So a high energy probe, and I can ask about the propagation of that probe towards the IR brane, but the momentum is such that the momentum is larger than this cutoff at the IR scale. So if I think of this as a particle and I throw the particle down this gravitational potential, if it hits the IR brane, by the time it hits the IR brane, it seems to have a momentum that is bigger than the allowed momentum in the 5D theory. So that is very curious. What actually happens to this probe? So that's the puzzle. And if we think about this, you might have some idea of what could happen, and you might say, well, a modest assumption is that maybe this bulk field, this phi field, has some kind of 5D self-interaction. It has a 3-point function, let's say. And that means that if I'm producing a high KK mode, and I have some 3-point vertex, it can decay into lower KK modes. And maybe those KK modes also can decay into even lower KK modes. And just with the modest assumption that there's some kind of bulk interaction, maybe even plausibly gravitational interaction, you can kind of cheat the intuition by allowing your initial state to decay into a shower or a multiplicity of many low energy states. So by splitting the energy, maybe this is a way to get away from this cutoff. Each individual particle that ends up in the IR is actually much lower energy. Okay, so maybe this is some way in which the cutoff makes sense. And here's basically all that we're doing. This vertex here is precisely a phi cubed interaction in the 5D Lagrangian. And this is almost the naive dimensional analysis estimate for what the coupling ought to be. The only thing that we're doing that's a little bit special is we are choosing the bulk. We're putting the bulk mass here as part of our scaling. This is just to ensure that at one loop level, the contributions to the mass of the bulk scalar are on the order of the parameter M phi that we put in. So this is a tuning of the theory. There is nothing about this as trying to solve any tuning problem. And here I'm being completely honest, I have introduced a tuning to the theory. And what this does, I mean, there's no KK parity, especially in the warped extra dimension. So this allows a bulk field to decay and undergo this cascade. Equivalently, this tells us that the 2-point function has an imaginary contribution because for any high KK mode, you can go into 2 lower KK modes and you can cut this and there's an imaginary part at loop level. Okay, so that's setting up that's all there is in terms of the intuition for what the phenomenon is. Okay, so it's a bit of an odd idea, but let's see it being put to work. So this is now our study on what we call soft bombs at colliders. So this is imagining that we have a collider and we produce this bulk mediator with a high form momentum, and we want to see what happens to it as it propagates down the IR brane, and we suspect that it cascades into a bunch of low energy particles. And in so doing, does that evade the EFT cutoff? This is now I'm going to have to get into equations, so let me be fully forthcoming. I want to be fully qualitative here.
Hello, may I ask some question?
Please, please.
So just would you remind me that you're assuming that all the standard model particles are located in a UV brane, is that right?
That's correct.
And so that they don't decay into lighter states.
That's correct.
Yep. And then I'm wondering about the gravity sector. What about the
Mhm.
graviton? Is it mediating towards the IL brane?
Good. So I have no intelligent comment about gravity. I know that this general idea has been explored before, where the KK graviton, for example, is an additional mediator for dark matter.
Yeah,
I don't
and
have the
to
reference for that.
I see. So it sounds like a sort of large extra dimension to me. So that's why I was wondering. So right.
Absolutely. So
Okay.
something different will happen. In fact,
Mhm.
one of the things I want to do is to see what happens in a large extra dimension as the analog to this. But something different will happen shortly.
I see. Thank you.
Unfortunately, we have to go through some equations before we get to that something different. In this slide, let me just say that there are some parameters in the theory, and let me choose to parameterize them in terms of a dimensionless bulk mass. So this is the mass of the field phi. This is the radius of curvature. This alpha is convenient because it's related to the conformal scaling dimension, and it ends up being the index of Bessel functions that show up. It's just a different parameter. There can also be brane localized terms. In particular, there could be a mass for the field. These can also be parameterized in a way that turns out to be convenient. I'm only mentioning them here because it's important to have them to control whether or not there's a zero mode. So this is to control whether or not there's a mass gap. Then one can write out the propagator of the bulk field in this form. And let me unpack that form. It's somewhat cumbersome. It's a bit of a pain to get, but so delta and G are the same, I apologize. It's a product of two factors. One that has to do with the UV brane and the position that's close to the UV brane. That's this factor here, this factor here. Another similar looking factor that has to do with the IR brane and the position that's closer to the IR brane. That's this factor here. And the denominator is just some momentum dependent term that depends on the UV brane and the IR brane. What you see here, it's a mess, but what you see here, there's a lot of Bessel functions, J and Y, and in particular, the combination of Z squared times the Bessel function. That combination shows up over and over again because this is the solution to the homogeneous equation of motion for the bulk field. And when you solve for the Green's function using the method of variations, you are perturbing about this homogeneous solution. This J tilde is simply what you get from the boundary conditions. And so this BUV is the boundary equation of motion acting on the homogeneous solution to the Green's function equation. So this is all to cobble together a propagator for the bulk field. You could have equivalently written this as a sum over KK modes. What's convenient is that this is in mixed position momentum space. So because we'll be talking about propagating from fixed Z positions to another fixed Z position, starting from the UV brane to the bulk, it's useful to have the 5D position explicit and to work in momentum space for the Minkowski directions. So this is all it looks cumbersome, but it's a convenient way of thinking about what I've been calling a sum over a large number of KK modes. Okay, one more semi-technical bit. Everything here is for the free. This is solving the kinetic term. This is the quadratic part of Lagrangian. This is solving it and getting the Green's function. That's the free propagator. One can also incorporate the self energy, and when here this delta is the Green's function including self energies, and you end up with this equation, right? So this term wouldn't be there if this were the free Green's function. It looks like something like the beta-salpeter equation. It's similar in spirit. And let me not dwell too much on the technicalities here, but you can check this for yourself by expanding about insertions of the 1pi diagram. But one can use this equation to see how does your propagator change when we take into account the dynamics of the self-energy? And this is the key. This is the underlying point about this opacity phenomenon, that why are we talking about warped dark sectors today rather than 15 years ago? If you expand this 1pi diagram in local insertions, right? So this is just an expansion in moments. The first couple of terms don't end up being particularly important. It doesn't change the free solution very much. But the second order term, which has two derivatives, so you would integrate by parts twice, ends up modifying the quadratic derivatives in the bulk equation of motion. So this ends up affecting the homogeneous solutions in a particular way that is rather illuminating. And here is the punchline. Once you take into account the 1pi diagrams, these homogeneous solutions change in the argument to the Bessel function. It picks up this imaginary part. It is as if we are taking our four momenta, which are real, and shifting it by an imaginary part, taking into account the fact that this thing has an imaginary part because there's a non-zero cut. This should sound somewhat familiar. Rather than having a bunch of KK modes whose poles are on the real axis, this shift is just telling us that the poles are actually shifted in the imaginary direction. And for higher KK modes, the shift is higher. This is simply saying that a high KK mode is unstable. It can decay. It has a non-zero width. That's exactly what this imaginary part is telling us. This is our usual dispersion relations in QFT. So higher KK modes have larger widths. That's exactly what this statement is telling us. And see, here is just some order one number, and Sylvain has some estimates, and Sylvain and my student Lexi have a more quantitative comparison coming out shortly. So what is this opacity phenomenon? This really boils down to the fact that when we started talking about these very narrow Breit-Wigner resonances, that was at tree level. Once you take into account the loop level self-energies, these Breit-Wigner widths become fatter and fatter, right? Because this bulk interaction that we assumed exists can cause high KK modes to decay, and if you have a very massive KK mode, there's a huge phase space for it to decay into lighter KK modes. And so these Breit-Wigner resonances smear out and fatten out into a continuum. And while this is related to the multi-particle continuum, this is, I think, conceptually distinct from a two-particle state. What I'm drawing in the red is really what would have been single particle states, except their widths become so large that it no longer makes sense to call them particles. This phenomenon, by the way, has been used by the dynamical dark matter folks, so Brooks and Dinez, to consider ensembles of dark matter, precisely like this, where the different dark matter species have different widths, and so they have different decay rates over cosmological times. Here, we're talking about a mediator. Okay, and that is a good intuition for what this separation between the discrete states and the continuum states means. For low energy, so if I produce a state here, it can propagate down to the IR brane and stay within the cutoff of the theory. For states with high energies produced in the UV brane, they don't get to propagate down to the IR brane, because if they did, that would seem to invalidate this EFT argument that the states with momentum up here should not be allowed to exist here because they're outside the regime of validity of the EFT. And it seems like what's happening is those states are high momentum, and because of these self-energies, they end up having large widths, and they smear out into a continuum. This continuum, we've just argued, is coming from a bunch of Breit-Wigners which have large widths, but they end up giving you precisely the same type of phenomenology that we argued you'd expect if the IR brane were not present. It's as if you're saying the correlation functions with high momentum don't get to know about the IR brane. It doesn't get to use the IR brane as a boundary condition, and therefore you shouldn't have a discrete set of KK states. So the story is piecing together rather nicely. And if this is sounding a lot like unparticle dynamics, this is not at all coincidence. Like this is very analogous to unparticle dynamics. So let me get to this story. So the story that we had started out with is, okay, so what happens? What is actually interesting about this? I produce this state, and now I have this idea that what ought to happen is I cascade decay. This happens because the states over here have large widths, and those want to decay into these things. And furthermore, because the widths are so large, it doesn't really make sense for this thing to be an asymptotic state. Right? This width is so large that it really wants to decay. Well, this state also is very large. It really wants to decay. This is in contrast to the narrow width approximation. In the narrow width approximation, when these bright Wigners are really tight, we would say that this decay process factorizes from the previous. This decay process factorizes from the previous. Now, because the widths are large, we don't get to factorize. And that's now something which will lead to some curiosity. All right. So Sylvain and Lexi worked out this really cool recursion relation. And I will walk through it at a high level rather than the nuts and bolts. But they wanted to figure out what the decay rate is for a decay into n particles. And the last one is this one with momentum p sub n. And relate that to what happens if that last particle has a branching. And they want to relate the decay rate for going to n particles to the decay rate going to n plus 1 particles. And so you can write that as an integral over phase space with the amplitude. And this blob here I'm writing as this curly A. I have to sum over the distinguishable final states. And you end up with an integral over this position U in the 5D. This is a 5D position U. So from the UV brane to the IR brane, all the possible places you can emit this particle, weighted by the wave function of the final state particle at that position U. So this is the amplitude M, this is M star. And there's a trick that ends up being really useful, that anytime you have a sum over these Kaluza-Klein factors, these KK wave functions, you can relate that to a sum over the poles of your spectral decomposition. So for any quantity A that has this form, you can rewrite it as the quantity integrated over this discontinuity. It's as if you're treating these poles as a branch cut. The poles merge into each other, which is intuitively consistent with the widths becoming large. So we can now write this sum over KK modes as an integral over the discontinuity, or this is again going back to the imaginary part of the 1PI diagram. So this is all the usual dispersion relation QFT that was taught in the 1960s, and now we no longer make a big deal about it in the 2000s. And with this trick, so let's not get into the details of the calculation, but with this trick, you can actually go ahead and calculate the decay width for going to n plus 1 particles. Lambda here is this triangle function that shows up in when you decompose phase space into two-body phase spaces. So this is a standard thing. And you end up with a relation of this form, that the rate to decay into n plus 1 particles can be related to the rate to decay to n particles times some ratio r, which is this ugly thing, but most importantly, it is small. Now, as long as the final states are in this continuum regime, as long as the final states all have fat widths, they don't get to be asymptotic states. So when I talk about this gamma n, it's not that, you want to decay into n states rather than n plus 1 states. You can't decay into n states because these n states tend to be not good asymptotic states. They have large widths. So they want to decay into more states, into n plus 1 states. You want to keep cascade decaying until you reach the Kaluza-Klein regime, where these things are all allowed to reach the IR brane. None of these states over here are allowed to be asymptotic final states. And so what you end up with this recursion relation is, if you have to go to n states, the rate for this process to occur, the rate for this entire cascade to occur, is like the small number to a power. So this lambda tilde is exactly this factor over here. This is the warped down cutoff at the IR brane. And this factor here is just saying you're taking the small number and multiplying it by itself, how many times you need to cascade in order to reach the closed decline regime. So I produce a high energy state here, and I keep cascade decaying because these things do not factorize and they cannot be asymptotic states. And I keep cascade decaying until I reach down here. And I end up with a exponential suppression of that cascade rate. And that now is a curious result, that these soft bomb events, these events where I produce this high energy state, and what does it do as it goes towards the IR? Well, it turns into this bunch of soft radiation, but that rate is actually suppressed because the narrow width approximation is breaking down in this regime where you have many KK modes. Okay, that's a lot of talking about weird things that happen in 5D. Now is the more fun speculative part. What is this good for? This is cute field theory, but what is this good for? And one thing that this may be good for is the annihilation rate of mediators. So if dark matter, for example, were on the UV brane, and I produce mediators. So a typical diagram is something like this. And I can produce mediators of different KK modes. The rate for this is typically set by these couplings. But if dark matter is particularly heavy, so here's dark matter. If dark matter is heavy, then the characteristic energy scale of these final states is very large. And if the energy being injected into these final states is actually in the continuum regime, then you get this entire story about the exponential suppression. And that ends up hitting your annihilation rate, right? You have to go through the whole cascade until you reach a valid asymptotic final state. But that cascade is suppressed because of the breakdown of the narrow width approximation. And so by playing with the bulk coupling, so the bulk self-coupling of this field, this lambda 5 to the cube, by playing with this self-coupling, I can control how much of this cascade contributes. I can control this exponential suppression. And that's now a new handle for playing with the annihilation of dark matter. Okay, so that's a curiosity.
Excuse me, I have a question.
Yes.
I'm curious what would happen for the lightest KK mode for phi, the zero mode for phi. Good. It looks stable.
Yes, so it doesn't even have to be the zero mode, but any states that are down here, so that are below here, are and okay, it's a continuum change, but any states down here, you can treat them as approximately asymptotic states. So I can talk about the first KK mode, the second K mode, and actually observing that in the IR brane. But the 1000th KK mode probably should not be an asymptotic state. So by playing with where this cutoff ought to be, or where the dark matter injects energy, you can play with that handle for annihilation.
I see. But if we wait for a long time, so that the all of the KK modes can decay into the lightest one, and then eventually we will get
I see.
the stable particles.
Good.
All.
That I agree.
That is that
I think, yeah.
Right?
Oh no, I see. No, so I am assuming that. Okay, good. So the main point is that some of the cascade you have to go through, and you pay a penalty. Once you get to the final states that are in this regime, they're effectively stable enough. They can be treated as final states. You're asking also, well, maybe the lightest one is actually literally stable.
Yeah.
It can be stable, or I can make it not stable. That's perfectly fair, but I'm not considering that as a dark matter candidate.
So then, to what that lightest state can decay? Is it?
Yeah.
Is there any possible mode?
I can put things. I can put things on the IR brane. Yeah, it's. if there are additional standard model states that it can access, it can decay on the UV brane.
I see. I see. For instance, photon can penetrate into the IR UV plane, IR plane, so that if I can decay into photons, something like that.
For example,
I see. I see. I see. Okay.
Yeah.
Thank you.
I mean, yeah, this is it's an interesting direction. That's not the main direction yet, but it is interesting.
I see.
Okay, so thus far, I've said a lot of really weird things, and it's kind of playing with field theory. I have this very modest suggestion for how it could be significant for dark matter model building. Let me now very quickly introduce something that looks completely different. 4-dimensional self-interacting dark matter. So my colleague Haibo Yu at UCR has really pushed this direction. The key point is if you have a mediator, so any type of dark sector, you end up with this long-range Yukawa force. And what this can do is you can exchange energy between dark matter. If dark matter can exchange energy when it scatters, that means in dark matter halos, the center of the halos can exchange energy. Typically at the center of the halo, you have a lot of slow dark matter that's collecting, and you form a cusp-like profile. But if dark matter can exchange energy, then the high energy dark matter that's near the outside of the halo that passes back and forth from the inside can hit the slow dark matter and exchange energy and thermalize it. So you end up with a cored halo. Why is that interesting? This can affect the observed stellar motions in galaxies. And so you have observational evidence for the dark matter profile, especially of small galaxies. And what you actually see is a whole bunch of small galaxies, so these are the dwarf spheroidals, which seem to be consistent with dark matter having a self-interaction on the order of 1 centimeter squared per gram, where this is the cross-section per dark matter mass, which is a convenient normalization. However, you can't just have dark matter with a constant cross-section because there are other constraints from clusters, galaxy clusters, which are much higher characteristic dark matter crossing velocity, which are more consistent with 0.1 centimeter squared per gram. And then you have observations like the bullet cluster that are strictly upper bounds. And so one of the neat things from the past 10 years has been this idea that if you have, purely 4D, if you have dark matter with a mediator, and the ratio of the masses is something like this, then by virtue of the mediator having a mass, you end up with a characteristic curve that seems to fit both the low mass dwarves and the galaxy clusters quite well. And this can even address these anomalies, a list of anomalies seen observationally. Okay, that's nice. Let me also mention that the structure of doing this calculation is actually remarkably rich. The calculation may either be perturbative, meaning you can use a Born approximation, or non-perturbative. If it's non-perturbative, if you're lucky, you can use the Coulomb scattering limit where the mediator mass is negligible. If it's non-perturbative and quantum, you get these resonances. So the contours here are the cross-section. The cross-sections depend very sensitively on the parameters of your theory because you end up hitting resonances or anti-resonances. In this case, there's no analytic expression, and it's numerically challenging to actually figure out what your cross-section is. And this is a plot just showing the phase space. So if I fix the velocity in the coupling and I play with the mediator mass, which is one of the parameters you have, your transfer cross-section for transferring energy behaves as this blue line. And there's a clear regime where it matches the Coulomb scattering limit. There's a limit where the Born approximation is good, which is what this yellow line is. And indeed, in this intermediate region, quantum effects are relevant, and you have these resonances. This is all a very nice 4-dimensional story. What happens in a 5-dimensional mediator case? So in a 5D case, you have a sum of different KK modes, T channel. Each of these are Yukawas with different characteristic ranges. And if we do the same trick that we did before with turning the sum over KK poles into a discontinuity across a branch cut, what you end up with is a potential that has a fractional power. And this is just really neat. This is something which few people have seen before, where this goes like 1 over r times 1 over kr for dimensions times a fractional power, non-integer power. There's some prefactor here, and This is a regulator taking into account that there's a mass gap, that this doesn't go down to 0. If there were a 0 mode, this would literally be a pure fractional potential. That's the factor here that controls it is the bulk mass of the field. And I think you can motivate this from the conformal argument recalling that this is related to your scaling dimension. And in fact, let me not spoil the story. It works. It turns out that you can do this numerically and you reproduce. So these are my student Ian's results, and this is the results from my colleague Haibo. You have a classical regime, but you don't have any classical approximation for a fractional potential. There's a resonant regime, and there's a regime where you expect the Born approximation to be valid, and it seems to be valid and consistent with numerics. That's actually very nice. And the behavior with resonances is somewhat subtle. This is just to say that if I look at the bulk mass as a parameter, so this is one of the parameters in the theory, you would expect that as I change the bulk mass, your cross-section, which is the y-axis here, should change monotonically. But because you hit these resonances, because the structure of the theory is actually really sensitive to these quasi-bound states, you get this non-monotonic behavior, right? So the color scheme is that decreasing alpha, decreasing bulk mass should go like the colors of the rainbow, the order of the rainbow, but that ordering doesn't follow over here. Okay. This is a rich structure that was there in 4D. It's a rich structure that's there in 5D. And in fact, maybe the punchline is that this all looks very trivially similar to ordinary 4D SIDM. The parameters are somewhat different, but in fact, because the 5D theory has more parameters, not just the mass of the lightest KK mode, but also playing with the profiles, there are many ways to get curves that seem to match the targets for self-interacting dark matter, as shown in the inset here. So it's both kind of interesting that there is a weird potential. It's also not interesting because, well, you have more parameters, so it's not surprising you can fit things. And here is where things get a little bit more interesting. One of the things that is true for self-interacting dark matter models is the moment you specify the self-interaction, you specify the strength of the coupling to the mediator. And what you typically find is that you can't get a thermal freeze-out dark matter candidate because the annihilation rate's too big. If your cross-section to annihilate is too small, you can play with that. But if the cross-section to annihilate is too big, there's no way to decrease it. That's where this opacity phenomenon comes in. So if I were to naively write down the annihilation rate in a 5D theory, you have to sum over all the possible final states. And here's the amplitude. There's this kinematic threshold here. But even without talking about this, we know that if my dark matter is heavy and I inject high momentum in my annihilations, I can control the rate for that by playing with the bulk self-coupling. This bulk self-coupling has nothing to do with the dark matter coupling to the mediator. And so it's a separate handle to control the size of the annihilation rate. And so you can apply this phenomenon, this opacity or censorship phenomenon, to dial down the annihilation rate and get self-interacting dark matter models that are also valid for thermal freeze-out. So that brings us down to the end. And let me just close with the statement that this is very much, I mean, this is an idea that we've been playing with and we're really excited about, and there are many things left to do. My student Lexi and Sylvain are coming out with a paper this week talking about the consistency with ADS-CFT. And the two that are really important, the interesting things I want to think about are cosmological bounds. And in particular, for dark sectors, particularly dark sectors with light particles, like MEV scale particles, one of the most stringent bounds is stellar cooling. Stars can radiate electrons that themselves radiate off light mediators. And if what we're saying is that radiating things at high energy can be exponentially suppressed because of this opacity, it seems like that's a way to reduce the stellar cooling bounds by suppressing the rate at which mediators are ejected from a hot star. And that was the thing that I found really tantalizing. And I will say that this is actually a little bit tricky because now it becomes a finite temperature problem where the actual geometry of the extra dimension ends up having to be deformed. So with that, I think I'm at time, and I want to thank you again for inviting me for this talk. Cheers.
Thank you very much. So if you have a question, then please turn on your mic and camera and ask. So question?
I have a question.
Mhm.
I think I missed something, but what kind of interaction of between mediator and standard model particles did you assume?
Good, good. Thanks. I may not have said that clearly. I am just assuming a Yukawa interaction, for example. So anything like that.
I see. So then that any, I just wonder if phi can decay into standard mode particles, just for instance, through the virtual high KK mode, right? Once it jump up to the high KK mode and then decays to the standard model.
Yes. So you're saying should you have decays that go like this?
Right. Yes.
Yes, exactly.
I see.
And that's the idea. Yes. So I think this picture people have played with in various ways. It's the thing that I think is relatively new is what happens with the bulk, the propagation in the bulk when you take into account this breakdown of the narrow width approximation.
I see. Okay. Yeah. Thank you.
Any other question or comment? Okay, then if not, then let's speak again.